Okay, well, welcome back, everybody. I thought the morning went pretty well. A lot of interesting discussions, and I hope we have lively discussions this afternoon as well. I'm sure a few more people, hopefully a few more people will be filtering in here for the afternoon session, but we should probably get started here just to try to keep on schedule. It is Friday afternoon after all, so maybe the full complement won't be coming back, but hopefully. So we're really glad to have Matthias Rempel give the first talk this afternoon. Matthias received his PhD in astrophysics in 2001 from the University of Göttingen, Germany. And in 2002, he began working at the High Altitude Observatory at NCAR in Boulder. And I believe he's been there ever since. And he's going to talk today about Flux emergence to sunspots, recent insights from modeling and observations. So the Zoom room is yours, Matthias. Take it away.
Yeah. Okay. So thank you very much for the invitation to give this talk. I hope you can see my slides.
Yep.
Okay. So what I'm trying to do here is giving a very short review of what we have learned from flux emergence simulations, mostly near surface simulations and some observational constraints. And of course, this review won't be complete, so please don't be upset if I don't mention everything. So I guess the generally accepted view of flux emergence is that we have magnetic flux rising from somewhere in the deep to middle convection zone towards the surface. And the reason for that is that observations show in the beginning a very strong horizontal expansion of the emerging flux, which is of course a reflection of the fact that the convection zone is heavily stratified. We have a density contrast of 10 to the 6. And flux emergence is pretty much about moving the magnetic field through the convection zone, but leaving all the mass behind. And there's a lot of mass to be left behind. And the consequence of this is that typically you get some relationship that the field strength drops with something of the density to some exponent. And that depends a little bit on the details. But in simulations, at least, you typically see something close to an exponent of 1/2. And you get this when you have primarily horizontal expansion of plasma as you move up. And what this means is, even if you start with very strong fields, something like 100 kilogauss, which is the strongest or near the strongest what people normally assume is present at the base of the convection zone, you end up with 100 Gauss in the photosphere. So in order to form sunspots, you have to find some process to re-amplify that. Then, of course, there are preferred symmetries, but I won't cover too much of that because this talk is pretty much about the near surface layers, and most of these symmetries come from deeper layers. And then after the sunspot formation, you have a quick transition also to the decay of sunspots. And if I get to the end of my talk, I will also talk a little bit about those aspects of the sunspot lifetime. So some reason it doesn't want to forward. Okay. So when we want to model flux emergence, there is a difference between the deeper part of the convection zone and the upper layers. And here I roughly draw the line at 20 megameters depth, but I mean, it's not a very strict discriminator. But when you deal with the deep convection zone, you have mostly subsonic flows. You can just use ideal gas equation of state. But the most important stuff is, the most important aspect is that the typical size of these flux concentrations, I call them sometimes flux tubes, but it doesn't have to be an idealized tube, just some concentration of flux. The typical size, if you want to have something with an active region flux, is smaller than the pressure scale height in the typical scale of convection. And that means is these flux concentrations that travel several times their diameter. And that means you have interaction with the ambient flow, and also the flows created by the rising flux is kind of the key to understand the dynamics. At the same time, you have only a small fraction, something like 100 out of the 10 to the 6 of the density contrast. And this has been modeled through various approaches, including thin flux tube approximation, anelastic models. and both with and without background convection. You have heard some of those aspects in the talks earlier this morning. So I would like to talk about the upper convection zone. Here you have the transition from subsonic to supersonic flows in the photosphere. You have to account for partial ionization. And if you want to model the photosphere pretty well, also three-dimensional radiative transfer. But the most important aspect here is that the size of these flux concentrations is larger than the scale height in the typical scale of convection. And this means you typically move a flux concentration roughly a diameter, and at the same time it has to expand by something like a factor of 10 to the 4. So the dynamics is strongly dominated by expansion, and most of the weakening of the field strength really happens in these surface layers, and this can be only modeled very well by doing fully compressible MHD with radiation transport and equation of state, which accounts for partial ionization. But it also gets more expensive. So very often this has been modeled in the past in separation from the deeper convection. So mostly due to computational constraints, but people have been relaxing these constraints over the past few years. Now, if you have a model which only deals with the uppermost layers of the convection zone, you somehow have to get the flux in there, and people have considered mostly 4 different setups. The first one is insertion of a buoyant horizontal flux tube somewhere in this box and just let it rise, and I've listed here a few examples of those. Another approach, this one was introduced by Bob Stein and Orke Nodlund more than a decade ago, is that they use an open convective boundary condition at the bottom. So they just impose a horizontal field in inflow regions and just let convection transport the flux into the domain. This is an approach where you try not to impose any structure to the field. The only degree of freedom is pretty much the field strength you assign to it, but everything else, all the scale separation happens entirely through the convection in the domain. And this is a best example of something like which one would call mostly passive flux emergence. Another class of models is the kinematic advection of some flux structure, which is very often idealized as a half torus through the bottom boundary condition. And these are models, so the advection is done kinematic, but it kind of mimics a little bit more what you expect from a picture of active flux emergence, where actually the emerging flux heavily modifies the velocity field in the simulation domain. And the last approach here is actually doing a coupling between a 3D convective dynamo model and the surface convection simulation. So these figures here show an example of the passive emerging active region formation Bob Stein presented. And what these models did show is that if you run them for long enough and emerge enough flux into them, you do form spot-like flux concentrations. Although in these models, they reach the size of a typical pore on the sun, but that is likely mostly limited by the extent of the domain, and these setups could be likely in principle scaled up, but it hasn't been done. But at least they showed just by having this passive flux emergence, you can form active regions in the solar photosphere. Now, the more active flux emergence simulations, here I show one model I worked with Marc Chung a couple of years ago on. They mimic a little bit more the picture of active flux emergence in the sense that they really drive with a rather rapid speed a flux system into the simulation domain. I mean, these boundary conditions give you a lot of freedom what you do, and they allow you to explore certain aspects. And what we tried in this simulation is we wanted to explore what is kind of the asymmetry you would get in the photosphere when you have a field-aligned flow, which is expected at least in flux tube models due to angular momentum conservation, but more recent convection simulations also sometimes have a field-aligned flow in emerging flux, but that has to do more, it comes more from the convective pattern, which actually transports the flux towards the surface. So what we did find in this simulation is when we have a field-aligned flow, and it goes in this simulation here from the right side to the left, so it would be retrograde. that you actually get a more coherent leading spot, a more dispersed trailing one, but you also find something which is inconsistent with what you see in observations. The leading spot forms actually later. So if I repeat this movie again, you can see this another time, that the leading spot has a delayed formation, mostly because there's so much mass pumped up there. You have diverging flows which delay the spot formation. Another interesting aspect is when this leading spot forms here, you see some indication that it actually forms top down. You see the first flux concentrations forming in the photosphere, and then they extend further down into the simulation domain. It's not that the strong foot point somehow makes it up into the photosphere. So one critical aspect in this simulation of the flux formation was the decoupling really of field from mass, and that happens pretty much through these formation of very small scale structure forming a lot of U-loop like structures which you can submerge, and you kind of leave the mass behind it and allow the larger scale flux to continue moving through the photosphere. And we did a more detailed analysis by essentially looking at the terms which contribute to the change of magnetic flux at a given radius, the flux transport through radius surfaces. So in the bottom panel here, we show how the flux surfaces evolve in the simulation. You see first these collapse of the flux surface here towards small radii, which is the flux, the sunspot formation phase, and then it transitions into a more or less self-similar decay, which is here approximated by just a Gaussian diffusion model by these dashed lines. Then we decompose these flows into mean flows and fluctuating components and radial and vertical ones. And what we found is that the contributions from vertical flows, which are shown here in this middle row, they are throughout the entire time, with a few exceptions, negative. So they always lead to kind of erosion of the flux concentrations. And then the contributions from vertical flows and horizontal flows have opposite sign, and they're for the most part balanced. And really what makes the distinction between sunspot formation, sunspot decay is a small imbalance between the two. And in the bottom panels, I do show this balance, but the scale is changed. The amplitude is artificially increased here by a factor of 10 to actually show it. So, and the other thing we learned here is that actually this correlation contribution is quite significant. Actually, most of the sunspot formation, except for the innermost part, comes actually from this correlation component. This has to do with these formation of mixed polarity, which converge. You have a negative polarity moving out, positive moving towards the spot, which leads to the positive contribution to the flux. This is what you see up here, and then you see the submergence of the U-loop, which is the negative contribution, which shows up in the vertical flows. So the takeaway is here, if you want to study how these surface flows lead to flux, to concentrational spots and decay, you really have to look at all components. If you, for example, just look at the radial transport of vertical field, you miss most of the thing which is going on here. Now, most of these simulations show sunspot formation as a very robust feature. Pretty much whenever you move enough flux into the photosphere, you end up with something of 4 kilogauss field strength. But having a computer model which shows this doesn't necessarily mean that we really understand how they form in detail. And the big question or the big problem here is that we have many processes which roughly happen on similar time scales. You have convective instability due to the superadiabatic stratification. You have radiative loss effects. You have the rapid cooling, which leads to pressure drop, but you also then drive flows around magnetic elements which are converging towards these elements, which means different elements actually attract each other. And then you have turbulence effects. And some of them I just discussed, and there's also some more exotic effects like the negative magnetic pressure instability people have invoked. And pretty much all of this happens in these simulations at the same time. These processes have similar time scales. So at least I'm not aware that anybody really tried to write it out and tell exactly which process contributes to much. It would require some idealized experiments, but you cannot really do it with these comprehensive simulations easily, which have all effects included. Now, I mentioned that these simulations where we push in magnetic fields are kind of an example of what one would maybe consider more an active flux emergence. And there have been important work over the past decade where people actually looked for the flows you would expect from such a scenario. And the flows you would expect prior to flux emergence is what is shown here in the lower right panel here, that you have a strong diverging flow in the photosphere and the uppermost layers of the convection zone prior to flux emergence. And then whereas people have looked into samples of active regions, and if you look something like 12 or 24 hours before flux emergence, you essentially see no evidence of such flows. Pretty much the flows you see around here are mostly supergranular flows, no strong evidence of flux emergence. So just by that, we know that these more active flux emergence, that is not happening on the sun. There might be a few examples where this is happening, but on average, these active regions don't show it. And then we went back into this model and just did a series of flux emergence simulation where we just decreased the rate at which we push flux into the domain. And in order to get to something which is consistent with observations, or I should say, which at least is not in a gross violation with observational constraints, there's still a lot of other inconsistencies. I mean, you had to dial down the flux emergence speed to something here like 70 meters per second in a depth of about 15 megameters, which is essentially comparable or even a little bit lower than typical convective flows. So based on this, it was concluded that flux emergence in the uppermost layers of the convection zone, it's mostly a passive process where flux is transported by the convective structures you have there all the time, and these structures are not heavily changed by the magnetic flux which is transported into the photosphere. Now, people have looked a little bit more careful, and there are a few other mysteries which I think are not fully explained at this point. So if one averages these pre-emergence flow field, something like 24 hours before flux emergence starts over a large number of active regions, more than 100, one actually sees that before flux emergence happens, you see on average actually a converging flow. You see a downflow region, which seems to have some east-west alignment, and the flux emergence kind of happens at the prograde edge of this. And so here on the left panel, this is actually the observation, and the right panel shows an attempt to kind of give an idea what this could mean. And what was done here is, so essentially the authors here, Aaron Birch and collaborators, they took the supergranular flow field and they assumed that flux emergence does not happen randomly in the supergranulation pattern, but in certain preferred locations. And then if you stack the supergranulation pattern on top of each other with that assumption, you can create a flow field which has some similarity to observed one. So this might indicate that perhaps that supergranulation has some effect on where actually emerging flux can make it through the upper layers of the convection zone. Another mystery is also that, I mean, this is related now to the larger scale symmetries of active regions, that Joyce's law is not established right at the time of flux emergence. Active region on average have no indication for tilt, and only in the later phase of flux emergence, when you have the strong separation of polarities, you establish actually the systematic tilt of active regions. Now, how this fits together with the different theories where this tilt come from is still an open question. I mean, one possible explanation could be that kind of the first parts of the flux bundles which make it through the photosphere, which have undergone this rapid expansion, maybe this rapid expansion wipes out most of the tilt signatures, and only in the later process, when the sunspots kind of settle above where their foot points deeper down are, then you see the establishment of tilt at the later times. Currently, we cannot do a direct comparison of this to flux emergence simulation, we would have to do large-scale flux emergence simulation with a sufficient realistic supergranulation pattern, which have rotation in there so that they have some preferences for tilt patterns. And at the same time, we would have to do a couple hundred of them to really average them together in a similar way it was done for observations, which is still a little bit challenging on the computational side right now. So the last part I would like to talk about here is flux emergence simulations, which are coupled to global dynamo simulations. And we did this experiment with one of Yuhong Fan's dynamo models, which did show the formation of buoyant magnetic structures which rise towards the surface. I mean, it's some combination of buoyancy and convection. It's not purely buoyant. And these structures are created in the simulation by non-azimuthal components of the zonal flows. And so the question was, and it has been for a long time, if you take these flux concentrations, which are created at least in some of the global dynamo models, if you move them all the way through the upper layers of the convection zone, which are not included in the simulation, do they actually form something which looks like active regions? One challenge we faced when we did this is, and you see it immediately when you look at these patterns here, they are way too large for typical active regions on the sun. So there could be two implications from this, that maybe the surface layers only let small parts of this come through and form active regions. Or the other possibility is that actually these structures are too large and these dynamo models do not produce smaller scale patterns which are more consistent with active regions. What we decided to do in this study is that we artificially rescaled this pattern and decreased it by a factor of 4 so that we have a computationally cheaper simulation which was easier to handle. But I just want to point this out, it's not 100% consistent coupling experiment in that sense. So this is work which was done by Feng Chen at HGO several years ago. So he took the magnetic field and flow pattern, imposed it at the bottom boundary of the Muram code, and it led to the formation of a complex active region with umbra field strengths on the order of 3-4 kilogauss. And you see here several patterns which indicate something which looks a little bit like penumbra. I get to back to this on the next slide, and also some indication of complex light bridges. And one important thing I also would point out, I talked before about these helioseismic constraints on the diverging flows caused by flux emergence. When you do this convective coupling, really, one important difference is if you look at these flux emergence regions, you actually see a lot of downflow lanes within this flux emergence region. So you have a much more balanced mass flux, which is different from these experiments where we moved a half torus through the bottom boundary. Where pretty much in the entire flux emergence region, you just have an upflow. And so in these sort of simulations, you have a more balanced vertical mass flux within the flux emergence region. So if you look at these pre-emergence horizontal flow patterns, they are consistent with what you with the limits which were derived from helioseismic observations. And one other aspect is also we see some asymmetry in the flux concentrations forming here. The leading polarities form first, and they are more coherent. That has to do with the fact that most of them are rooted kind of in the leading edge of these downflow lanes here, whereas the trailing polarities form more above some upflow regions. Repeating this experiment at higher resolution, you see now in the photosphere very complex light bridges forming in these active regions. Some of them, like this example here, you see a very thin light bridge with a central dark lane, and other light bridges show convective patterns as it is seen also in light bridges on the sun. And you also see these structures here, which do look like penumbra, but before you get too excited about it, they have this one nagging inconsistency with observations that actually the Evershed flow goes the wrong way. You have a converging flow in these regions. And at least we have not been able to find really a transition to an evershed flow in these simulations. So this remains an open question. And if I don't run out of time, I might say a little bit more about it towards the end of this talk. So most recent work, in particular by Japanese group Hideyuki Hotta and collaborators, has focused on flux emergence simulations, which actually have no domains which include the whole convection zone. I mean, not the whole in terms of horizontal extent, but in terms of vertical extent, using a code which also has radiation transport or somewhat simplified radiation transport in the photosphere. And with these simulations, they were able to form rather complicated active regions, example of data spots here, which have strongly twisted light bridges with feed strings of up to 7 kilogauss in this case. Another interesting follow-up study is the work by Takafumi Kaneko, who did use the same setup, but he varied the location where he put this initial flux concentration. I think he did something on the order of 100 different experiments, and he found that what you actually get in the photosphere depends very critically on where you place your initial flux tube. And this is just another piece of evidence which shows it's really the convection which heavily influences flux emergence. It's mostly a passive process, but it also tells you, in order to have a consistent picture of flux emergence, you really have to worry about how these flux concentrations are formed in the first place, because you don't really have this freedom to put the flux anywhere you want in the pre-existing convection pattern. You expect certain correlations with the convection pattern and the flux concentrations you're getting. Okay, so now I would like to talk a little bit about details of sunspot structure and the open questions. And actually the most nagging one is really, why do sunspots have a penumbra? And while we do have some simulations which show pretty decent penumbra, this question is still not really settled, because you only get the penumbra if you really massage your setup in the right direction. And I show here a movie where I just go back and forth between two different top boundary conditions. When in the case when I have a penumbra, the feed is artificially made more horizontal at the top boundary, and then if I switch back to a potential feed, the penumbra evershed flow disappears in about 20 minutes or half an hour. And if you switch the boundary condition again, it comes back over roughly the same time scale. And so in some sense, in all of these simulations, we can create something which looks like a penumbra, but it doesn't come fully self-consistently out of these setups. And there are a lot of different reasons why this might be, and there's not really a convincing solution. There was one suggestion a while ago by Orkenotlo that perhaps having a more concentrated foot point and having feed fanning out more might help penumbra formation. And that is something which looks promising to some degree. But first, I want to go back to this issue with imposing a horizontal field. I mean, is there any possibility that actually the sun might do this? Because there is sometimes people have found in chromospheric observations, like this work by Shimizu, some indications that there might be some precursor of penumbra formation in the chromosphere before you see it in the photosphere. Now, if you compare the field strengths you do find at the boundary between umbra and penumbra from Hinode observation, you get something about 1,800 Gauss. There is some discussion how universal this field strength is, if all sunspots have it around that value, or if there's some variation. I'm not getting into that here, but the work which was done here is actually using different simulated sunspot models. All the three panels on the right are sunspot simulations, and evaluating this value. The two on the left here, these are models which have a potential field, which gets something still a little bit short of the 1.8 kilogauss, but somewhat close. But if you artificially make the feed more horizontal, you do have at the penumbra boundary a field strength which is significantly lower and not consistent with observations. So the sun doesn't seem to play this trick. So what are the other possibilities? The possibility is the subsurface structure of sunspots, and this is work which was done a few years ago by Marc Panya at the Max Planck Institute, working there with Robert Cameron, and they set up sunspots with a subsurface structure which was heavily fluting unstable. And they could show that when you have these fluting instability happening, it promotes penumbra formation. You do get a more extended penumbra, but you also have the problem that this fluting instability doesn't stop. It propagates and really takes the sunspot apart. And at some point you see kind of these radial light bridges entering the spot, and eventually it would fall apart. So this is a promising approach. It definitely shows strongly that the subsurface structure of sunspots may be a critical element in understanding the penumbra, but it looks like also here one has to do some tuning of the setup. You want to have some fluting, but you also at the same time want to constrain it to not move too far. Of course, the fluting instability certainly will play a role in the decay of sunspot. And what I show here is one simulation where I actually wanted to study the sunspot decay, but the simulation decided to not decay, which is a very interesting aspect on its own. But what I want to show here is when you run these simulations for long enough, you do see fluting instability. You see these intrusions of regions with weaker feed, which do show up as something like light bridges. And what happens here is that the umbra of the spot gets corroded by the fluting instability, but the presence of a penumbra at mode regions prevents the decay of the overall sunspot. So you get a more and more fragmented umbra, but the sunspot as a whole is kept together by the penumbra. And this was studied by Hannah Strecker a couple of years ago. She analyzed fluting instability in the sunspot simulations. She found the top layers are stable, and this is expected based on work several years ago by Meyer et al., that essentially the buoyancy of the penumbra stabilizes the spot against fluting. Then it's most fluting unstable in a depth of about 3 megameters, and then it becomes more or less neutrally stable as you go down. So as the sunspot evolves, the umbra is more and more kind of corroded by the fluting instability. In this case, the sunspot was not allowed to decay due to stabilizing effect of penumbra and mode flow. But if eventually the penumbra would disappear, such a spot would very rapidly disappear. The umbra would decay as well, since it has been already corroded by the fluting instability. That brings me to the end of this talk. The main takeaway here really is I would like to highlight that over the last decade or so, we have really seen this transition from what one would call active flux emergence to more passive flux emergence. And passive means that most of the transport, at least in the near surface layers where we do have observational constraints, seems to happen with the convective structures which are there all the time. And these convective structures are at least not modified by the magnetic flux passing through to the degree that it would lead to substantial observable effects in the flow pattern. Penumbra formation is still some big mystery, and so it looks like in simulations we can get decent penumbra if we pick the setup the right way, either by boundary conditions or by subsurface structure. But it's a little bit discomforting is the fact that it's extremely robust on the sun. The sun gets this right pretty much most of the time. There are not too many spots with a failed penumbra. So why do we have to do something special in simulations? What is really missing here? That's still an open question. Okay, thank you very much.
Thank you very much. Very interesting, Matthias. Questions, folks? While people are raising their hands, there were a couple of questions in the Jamboards. There was a question actually for Bob Stein, if he's here. In the Stein advection of horizontal field approach, what sets the active region scale? Is it dependent on the box size, basically, is the question? Or
I think it is mostly the depth, because the depth of 20 megameter gives you the largest structure. So I think that that's what's setting the scale. And
Okay. Thank you. Do we have any raised hands here on Zoom? If not, there's a question in the Zoom chat from Gustavo. I think the question boils down to, is the flow considered an input condition for the simulation, or are you just imposing the magnetic field?
This is regarding the simulation with in combination with the simulation of Yu-Hong Fang. If you consider only the magnetic field or also the flow.
Yeah, so in that simulation, yeah, we imposed both flow and magnetic field at the bottom boundary. And so the coupling imposes both the horizontal and vertical flow components, but for the magnetic field, of course, you only transport the horizontal field, the vertical follows automatically from it. If you do all three, you get a little bit of oversubscription of the system.
There is a following question to that from the chat also. So did you try only using the magnetic field, and there is any consequence of using both field and flow?
I think we only consider doing the full coupling of field and flow. I mean, only imposing the field, I mean, that would get a little bit more in the direction of Bob Stein's setup, right? You would impose some field structure at the bottom boundary and then use the convective flows, which are just present in the simulation all the time, to slowly carry it in. It's certainly something one could try as well, but we haven't done that with that setup.
David?
Yeah, Joy's law tilt. In your simulations, do you still favor Coriolis force on rising tubes, or is this an underlying orientation of the field that's emerging?
So the simulations I've been doing, they're just near surface layers, and we normally don't include rotation. So we don't have Coriolis force at all. I mean, but I guess global simulations which do show this formation of flux bundles, it's in general a combination of Coriolis force acting on these rising bundles, but also simply the tilt which is present in the convection pattern, which is transporting these as well. It's a combination of the two. And the more passive it is, the more it is just whatever pattern is present in the convection.
All right, thank you.
Bob? Bob Stein, you have your hand up.
I wanted to mention another simulation that we did that took off from the one that Matthias showed, where we allowed the field at the bottom to increase to 5 kilogauss. And then what we found is that the small scale structures coalesced into a sunspot looking structure, again, without a real penumbra, as Matthias said, because of the top boundary condition. And in the process of them merging, you get very realistic light bridges.
Spacey.
Okay. So to follow up David's point, so do you think then, Matthias, that the convection then while it doesn't explain the Joy laws, it's basically responsible for, you know, all the spread, right? So in order to really understand Joy's law, we need to be able to have more physics, is what you're saying, larger scale.
I mean, yeah, I mean, you have to really do the full thing.
Yeah.
Go deeper in the convection zone. But I mean, interesting is, I mean, these observational mystery, I showed you that at least in the early stages of flux emergence, the first flux which comes through, it doesn't seem to show on average a preference, and it only is established later. So why is it that the first parts of the flux bundle which make it through kind of these preferences wiped out and it's later established? I don't think we have a consistent model for this, but some ideas what it might mean.
Okay, Bob, I see you still have your hand up. Did you finish your question or?
I'm done.
Oh, okay. Aimee?
Hi, thanks for the talk. Yeah, so I wanted to ask about coupling simulations from a global model to a more near surface model. You were part of the work with Chen to do that, correct?
Yeah.
And so, I mean, definitely buoyancy is driving the rise in the lower layers for the global simulation. Is that correct? It's not passive at that point, is it?
It's some mix. I think Honk in her paper has likely some analysis of it. It's some mix of some buoyancy, but also just transport by whatever larger scale convection patterns are in there.
Oh, okay. All
In
right.
particular, these patterns we pushed into the Muram domain, they had kind of these hairpin-like structure that had to do with kind of the banana cells present in this global simulation, kind of stretching out those features, wrapping them up a little bit and bringing them up at the same time.
Okay, and then ultimately to get the right size scale on the surface, you just downscaled it, right? You just, yeah,
So,
okay.
I mean, but there's an interesting question, you know, are these structures we see in these global simulations, are they just too large? Because we know that all these global simulations, they have too much convective power on large scales. So maybe that's the reason why they also create magnetic structures on too large scales.
Okay.
So, I mean, if we would have moved that entire thing into a Muram domain, I mean, apart from computational expense, it would have been, I mean, likely more something what you see on other fast rotating stars, not what you see on the sun. But of course, there's also the other possibility that maybe the sun has these bigger structures, but then in the near surface layers, it only, things are conspire only in certain locations that something on a scale of 1 or 2 supergranules can get through and the rest is kind of kept down. I mean, that possibility exists as well.
Okay.
But for minimizing computation expense, we just decided we scale down and deal with a smaller box.
Okay, thank you.
Nick?
Yeah, I think this idea or this question of what does convection imprint on a tube rising through the convection from rotation is a very interesting question. The graduate student Jacob Nunwade is maybe here, but he's working on some of this sort of stuff as well. But you know, a lot of the original ideas for Joy's tilt sort of that were ideas that completely ignored convection, right? You had a nice little loop that was rising with a Coriolis force and it had legs and that twisted a little bit and there you go, right?
Yeah.
Those things, if you stick one of those things in convection, then it gets mangled very, very quickly. And you have bits going all over the place doing all kinds of stuff. So it's kind of interesting to ask under those circumstances, why do you always get things of one particular sign emerging? So I'm interested by this idea that Matthias, you mentioned that, yeah, it doesn't matter, stuff just comes to the surface and then you organize it at the surface. You know, it happens later, actually during the emergent process. So that would solve that problem.
Yeah.
What we're seeing so far is that, you know, it's such a, you know, stochastic process that trying to pull out any statistic which is coherent is very difficult.
Yeah. I mean, there is certainly this idea that, I mean, if it emerges to the surface without any tilt, and then you have the separation of the two polarities, you have certainly Coriolis force acting on that, but maybe Robert Cameron is still here and can comment on it. My understanding was that while this might make a contribution, that effect alone would not be sufficient to explain the active region tilt we see on average.
So I can comment, yes, the numbers work out. That would work, but you cannot exclude other things. But those numbers are fine.
Okay, that's good to know.
Okay, Todd, did you want to ask your question?
Sure, I can ask it out loud. I think so. If there are these large structures underneath and they're sort of ubiquitous, but probably not exactly ubiquitous. Is there any way you could detect them? Would there be a thermal signature or something that we could see with the seismology or a change in other convection patterns that resulted that would somehow imprint itself on the surface?
I mean, I hope I can pass this question on to somebody who works in helioseismology, but from my understanding, it would be a really tough thing to do.
Okay. Irina?
Yes, thank you. First, thank you, Matthias, for great presentation. Very interested. I have two questions. Let me ask first Bob Stein. Sorry.
There is an echo in your side.
Yeah, you might want to turn your volume down a little bit, Irina.
It is better now?
Yes.
There you go.
Okay. First question to Bob. You mentioned your second model of flux emergence. If you can post reference to your publication, I will be really appreciated. And my second question to Matthias regarding Evershed effect. If I remember right, your early simulations of sunspots, you had very realistic Evershed flows when you keep penumbra size by upper boundary conditions. But you mentioned some problems with Evershed effect in the case of flux emergence. Can you discuss what can be a potential reason for this?
So in the flux emergence simulation, we used the potential field boundary condition. So we did not play this trick of imposing a more horizontal field. And in that case, it looks like you get these converging flows, and they look pretty much like those converging flows. They are siphon flows for the most part, whereas the Evershed flow you get when you impose a more horizontal field is really more a deflection of the overturning motions you have in granulation in the presence of the inclined horizontal feed in the preferential outflow. Now, the interesting thing is, in some of these sunspot simulations, like the one I showed in the end, which I ran for very long, you actually see even in those simulations where I impose a horizontal field, sometimes some patches of the penumbra, which for a certain amount of time, for a few hours, change the flow direction to inverse Evershed flow. And then after some time, they transition back to the regular Evershed flow. So there seems to be some bistable solution there. You can have both flows, and you might just have to find something to shift the preference from one to the other one.
Yeah.
So we'll do one more question here to try to stay on schedule here. Leif? Oh, you need to unmute.
It's well known that the large-scale magnetic field on the surface is organized into large-scale structures, like also known as the sector structure, that is very stable and often lives for years on end. Is that something that Matthias wants to comment on? It presumably will come from below the convection zone, because I don't think we can have a memory in the convection zone. But if you impose a large-scale structure at the bottom, what will happen when you simulate that?
I mean, I would like to ask actually a related question to those people who actually run surface flux transport models. If you kind of extrapolate this field up into the corona, and so do you actually, by just using those ingredients which are present in the surface flux transport models, do you reproduce these longer lived structures? Or is there something missing in that picture? Because I think this goes really to a little bit larger scale than just these active region focused flux emergence simulations.
Well, anybody taking that?
I think the flux emergence models rely on what kind of patterns you put in terms of where the things emerge. So you're not going to get an independent reading on whether there's a large scale structure.
But the question, I want to ask is, if you just take the active regions as they emerge and then just move them around, I mean, do you get something which is consistent with these larger scale structures, or is there still something missing? And I think Robert has a hand up.
Yeah, so we haven't looked is the answer. We should look, but we haven't. And I don't know anyone who's looked. I don't think it's been looked at. The whole sector structure is one of these things which people haven't looked at, although they probably should be.
But what do you mean by moved them around?
So the question is, where does this sector pattern come from? And if we believe the surface flux transport after emergence, then it's all fixed. So it must be in the emergence pattern. And the question is, what exactly in the emergence pattern would it be? And is it there in what we have at the moment, our SFT simulations? And it's a relatively simple question to answer, but no one's done it. I haven't done it. Yeah, bad ass.
But with surface flux transport, you do see the production of large unipolar regions that persist for months, if not years. So,
so the question is this, how does this relate to the sector structure? And this particular question, I think, is still not addressed. It's something we could do. We just need to go back and do the analysis they did with the observations in terms of the sector structures. And that would be, I think, interesting. Marc DeRosa has a question.
Well, I don't have a question, and I don't have an answer either. All right. But also, my original thought was that the nesting may play a role in preserving the large scale structure, but I think it's also the case that the large scale structure just doesn't really. I mean, like thinking of it in terms of circular harmonics, the lowest degree harmonics don't really evolve very much or very quickly. And that's typically what you're seeing in the sector structure, as Life very well knows, of course. He's thought about this longer than I have, that's for sure. So I think it's just a matter of the fact that those low degree modes are not really evolving very quickly.
So I'd like to, at this point, really quick, so we don't get too behind on the schedule. Sasha, are you here? Looks like you are.
Yes,
Sasha?
yeah.
Okay, great.
I've been
So
waiting.
Sasha,
Actually, I have some answers to questions to discuss now, but I prepared a presentation, so
sure.
let me just share my screen.
Okay.
And so can you see it?
Yes, we can.
Okay, let me just make it full screen. I actually do have some answers to Life's questions, but I prepared kind of presentation and based on a recent paper that it just appeared a couple of days ago in archive, so you can look in more detail of this. I have only 10 minutes to present it. So I'll be try to again to that interesting questions we discussed. What about the relationship between bipolar magnetic regions and the dynamo, global dynamo? And we discussed two models today. One of these Babcock-Clayton model, which is based on primary element bipolar magnetic regions. They emerge from tachocline, from base convection zone. Then due to the tilt, that they have a flux disbalance, which is transported by meridional circulation to polar regions. And then magnetic flux emerges into the tachocline, where it's amplified, generate a toroidal magnetic flux, which again emerges in the form of bipolar magnetic regions. So it's controlled by meridional circulation and by amount of flux transport on the surface. And justification is that we see a quite overt migration of emerging bipolar magnetic regions. The alternative theory is Parker's theory. And here it's in this theory, the dynamo cycle starts from generation. It's how described by Parker in a paper 1955, generation of polyidal magnetic field at high latitude, 60 degrees latitude, by cyclonic convective motions alpha effect. And then polyidal magnetic field transformed into toroidal field by differential rotation, omega effect. And then latitudinal migration of the magnetic flux explained by dynamo wave traveling along surfaces of constant rotation. And in this case, structure of meridional circulation is not important in this model. And the near surface shear layer provides conditions for equator word migration of bipolar magnetic regions at the surface, explains the butterfly diagram. So this dynamo cycle is predominantly controlled by cyclonic convection, differential rotation, and turbulent diffusion. So the justification is that this dynamo model is supported by 3D MHD simulations. And all simulations show that Parker's model is valid. And also is supported by helioseismic observations of torsion oscillations. And these are the big structures that what Todd was mentioned that we can see by helioseismology, and they tell us about the dynamo and emergent flux. So I played just movie of torsion oscillations. So this is a zonal acceleration from MDI and HMI, and we can see kind of two waves. So the zonal acceleration reflects a magnetic field, thermomagnetic field, and we can see two waves. One is they originated, as Parker predicted, 60 degrees latitude, and one of these waves migrates towards the equator. This blue, it corresponds to the magnetic field band with zonal negative zonal acceleration, deceleration. And also we can see migration to the polar regions. But the question is, what is the role of bipolar magnetic regions and surface flux transport in this model? So we developed a model which includes formation of bipolar magnetic regions. So this model we've been developing Valery Pipin. Most of Valery Pipin developed all these computer codes for the past solar cycle. And it's a full nonlinear mean field model. It includes three-dimensional magnetic field and current version two-dimensional flow field. And also it includes energy equation, the heat transport, and all is formulated in terms of the mean field theory. So the turbulent effects are modeled here separately. There is kind of coefficients in the large scale equations. And the turbulence theory is used to model this interaction of turbulence with magnetic field and large scale flows. So it includes also magnetic helicity. And it's important that it includes the effect of magnetic field on convective heat transport. So this model was published by Valery earlier this year, a few months ago. And it includes, the newest model includes bipolar magnetic regions. Its formation of due to the magnetic buoyancy instability. So this model explains that what we found that with more effects we include and more observations we can explain, and particularly it explains the torsion oscillations, not just torsion oscillations, but also extended solar cycle of torsion oscillations. And Roger asked this question about what causes this and this extended solar cycle and the polar branches. And what we found that the primary driver is a magnetic field. But then there are some magnetic fields, not just a Lorentz fault, but magnetic field also affects the heat transport. And then modulation of the heat transport by magnetic field modulates the meridional circulation. And then modulation of meridional circulation produces additional modulation of the torsion oscillations and causes the extended solar cycle. So that's why we see when there is no even that on the surface, no magnetic field, no ephemeral active regions, you still see torsion oscillations. You can still see variations of the meridional circulation. It's not just inflows. We see that even outside active regions, we can see these bands of migrating bands of variation of meridional circulation. So also models explained Waldmeier relation and what was found when the initial model was calculated that bipolar magnetic regions contribute to the dynamo cycle, but in terms of the duration and the strength, it's at about 10–20%. That what if we put some constraints on some amount of magnetic flux emerge from the surface. So this is just shows that for dynamo waves how they propagate inside the sun, and how we modeled the flux emergence. Here that the magnetic toroidal field is the strongest, then it may become unstable due to the magnetic buoyancy instability. So here we used this criteria is already discussed by Gustavo for magnetic buoyancy instability. That's Parker-Gilman criterion for the instability. And when we look at these dynamo waves in the convection zone, we can identify the points of instability, but the regions, basically the here that this criteria is plotted as a function of depth here, and we can see here some points where the flux becomes unstable. So we know distribution with depth of the unstable points, and basically that's the age of the dynamo waves. They travel through latitude and radius, but then how it's distributed with longitude, latitude, we don't know. So the first the model was put random distribution with latitude, longitude. And it's and that's what how this effect was 20% effect was obtained from this. And that what recently we tried to actually to model the solar cycle 22 and 23 by imposing perturbation. So instability is initiated by producing some upflows at this point. And so that the strength and the size of upflows corresponds to the size of active regions that we see that emerge on the surface of the sun. And the distribution of latitude, longitude was also taken from observations of sunspot regions. But then it's in the model, actually this effect of the bipolar magnetic regions in the midfield theory is modeled in terms of additional electromotive force, which includes two terms. One term is T cross B, that's just buoyancy. And the second term, it's subsurface alpha effect, which creates, which models the tilt of active regions. And Marc showed that this term equivalent, the tilt is equivalent to subsurface alpha effect. So that's how it's modeled. So this is an example of emerging active regions. So they essentially start emerging as bubbles that Gustavo showed, but then you can see here that close to the surface, the kind of bundles of magnetic field lines. And this is relatively low resolution model, but we can see that formation of bipolar active regions. It's one of them here, the time is in days in this movie. And then it's another movie that shows that how it's evolution of magnetic field. And here actually the movie at the bottom right will show the magnetic field at the source surface. So that's the question that life asks, how it reflects the large scale structures. And here that what I forgot to tell that what we found that magnetic active regions can emerge from the deep convection zone and from the bottom convection, from the top convection zone. And what we found that magnetic active regions that initiated the buoyancy from the lower half of convection zone, they don't emerge on the surface, but they contribute to the non-axisymmetric large scale non-axisymmetric magnetic field. And that produces the long-living non-axisymmetric structures that we can see in these surface models in heliospheric field. And only active regions that initiated at, in the upper half of the convection zone, they emerge in the form of bipolar magnetic regions on the surface. So here you can see the simulations now at the time in years, and you can see this at the bottom right. You can see heliospheric this surface calculated from these models, and also you can see that what also how this magnetic field on the surface evolves during cycle was 23, now cycle 2024. And here it's a movie of polarity reversals. And also the emerging active regions, they form original model is axisymmetrical and not now symmetrical, but the emergence of active regions creates north-south asymmetry, not only in bipolar magnetic region, but also in large-scale magnetic field. So here that what this kind of a spiral magnetic field, this is it's a radial magnetic field here that shows it's a kind of spiral structure in polar regions. So also what we compared with some distributions that known from observations, distribution of magnetic flux, bipolar, that active regions that emerge with area, that kind of a power law, and also distribution of so that after emergence, analyze the inclination of bipolar magnetic regions and compared with Joyce law. And it shows that it's it indeed at high latitudes kind of a saturation of Joyce law that some observations showed. Also, we look at the distribution of flux in terms of the flux distribution of emerging active regions with flux. It's a power law, but in observations the power law is flatter. That's what Clara Parnell found some years ago, but still it kind of shows the power law also this this model. And just finally, what I show. The comparison of magnetic butterfly diagram. And here we can see that some impulses of solar activity that was observed during the cycles. And the model doesn't reproduce exactly these impulses. And one of the reasons maybe because we used just random distribution of the tilt. it's amazing, but we didn't find a database where that magnetic tilt will be computed for these two solar cycles consistently by the same technique. And so it was tilt was just random, but still it shows that some kind of similarity of in the magnetic butterfly diagram. So it's in conclusion, this initial result shows that only bipolar magnetic region perturbations that located in the upper half of the convection zone lead to magnetic active regions on the solar surface. And while these magnetic regions initialized at the lower part of the convection zone don't emerge, they affect the global dynamo process that create these large-scale structures, contribute to non-symmetric large-scale structures. So its result shows that bipolar magnetic regions can play a substantial role in this Parker's dynamo process of solar cycle. And that also what we look at, we try to explain that this long period of low activity between these two cycles, and also try to find while this cycle 24 is much lower than for cycle 23. And we found that bipolar magnetic regions cannot explain this. We still need to some kind of reduction of global alpha effect in the declining phase of cycle 23. So it's something that it affects the global circulation, the global convection of the sun. Okay, so thank you. So that's all I wanted to show.
Thank you, Sasha. We have time for maybe one or two questions. Leif?
Yeah, all that is very nice, but does not explain or even get close to the main problem, and that is the stability and long-lived nature of the sector structure that can last for years. And so there's still a problem there. And
no, it's still far away. So what our goal is finally to get some kind of, it's a field theory. And the final goal is to get, it's something to better understanding of three-dimensional simulations. And three-dimensional simulations, we still use field theory for interpretation, but still we don't quite understand the interaction of turbulence with magnetic fields. That what in this model theory, this interaction is modeled in some approximation, scale separation.
Robert, did you have a question, or did you put your hand down?
Yeah, I had a question. So as to the difference between cycle 23 and 24, if it actually used the data for the tilt angles, and I think they were available from MWO at least for cycles 22 and 23, then
Robert, if you send me a reference, I would appreciate this. We found that separately, for cycle 24, say Aimee calculated this, but it's important to use the same technique. That what we think we calculate with Stenful of cycle 23, but allow this data because of this crash.
Yeah.
So
and my other question was, I guess your conclusions are very model dependent.
That it's in a sense they are model dependent, because we have to initiate the flux emergence to match the flux that we can see on the surface. That already that Nick Bramell asking, that instability can happen everywhere. Why we see only some events of these, and probably something relates to some deep convection. So it's in this sense, that when you initiate this instability, you put some initial conditions, and this model depends on this, right? So that's so it's obviously some free parameters here.
Okay, thank you very much. So let's move on. Our next invited talk is given by Marc DeRosa, who got his PhD at the University of Colorado Boulder in 2001. And he's been at Lockheed Martin and Palo Alto ever since, I think. So Marc, the Zoom room is yours. Take it away.
Okay, thank you. And yeah, thanks to Bill and Aimee for asking me to talk a little bit about global scale modeling. Some of this I'm going to be talking for the first half of the talk on flux transport models, which is a well-traveled road, and on that road there are many cottages. It's a cottage industry to create these surface flux transport models. I'm in one of the cottages. David Hathaway and Lisa Upton are in another, and the Max Planck people are probably in yet another cottage. So I'll try not to spend a lot of time on that, but let me just emphasize that you know, the magnetic field is basically structuring all scales from small to very large. And on this AIA movie here, you can see a flare goes off and it sends out this blast wave, at least to the northern direction. And by itself, this looks somewhat localized, but then if you look on larger scales, so here's the full image from that, and you do one of these difference images like this, you'll see that in fact, when that flare went off, the blast wave actually goes a pretty far distance along at least along the photospheric and then the coronal regions. From the location of the flare. And we have other flares that actually show an even more global nature. And there's been some evidence that sometimes one dynamic event in one place can trigger dynamic events in other places. So it's important to understand how the global dynamics of the magnetic field operate. And so the only issue is that magnetic fields are really not very easily observed, except on the photosphere, more or less. You can definitely find observations in other places, in particular in the corona, but they often have a pretty low spatial resolution and also low temporal resolution. And we've definitely found that, especially in the lower levels of the atmosphere, that energy can be transmitted on some fairly small scales. So it's important to have the right spatial and temporal resolution to understand the evolution of the magnetic field. The other thing is that photospheric observations provide basically a pretty significant number of constraints, particularly on the dynamo, but also on other things as well, like the evolution of the overlying magnetic field. And some of those constraints are listed on this next slide, which is sort of a laundry list of things, but it includes everything from, you know, the well-known butterfly diagram and Joy's law, tilt angles, Hale's law, polarity reversing, and things like that. And then there's these correlations between, like, the amplitude of one sunspot cycle and its period, or the amplitude of one sunspot cycle with the strength of the polar fields during the preceding minimum. The shape of the cycle seems to be important. It's slightly asymmetric, comparing the ramp up and the ramp down phases. There's clearly some hemispheric coupling. Both the northern and the southern hemispheres are mostly in sync. They never really get very far out of sync, but then there's also some hemispheric asymmetries. In particular, it's well known that activity maxima in the northern and southern hemispheres often can differ by a significant interval of time. So all of these things are providing us with some clues to what's going on in the interior, and I think it's you know, our challenge, in particular as part of COFFIES, is to try to gain a better understanding of these things. So for this talk, I'm going to mainly talk about two topics. One is the global surface flux transport models that I'm using Carl Schreiber's code that he developed basically at about the time that I arrived at Lockheed. I was thrown into the fire, so to speak. And then more recently, we've been thinking about electric field driven models, which potentially can provide some more information about the energy flow through the photosphere into the higher layers. So let's see, let me get going here. Okay, so most surface flux transport models, you know, have a bunch of ingredients, and these ingredients primarily are constrained by the observed dynamics that many of which I had mentioned earlier, and these include dynamics associated with flux emergence, the large scale flows such as differential rotation and the polar meridional flows at the photosphere. There's the diffusion or convective dispersal process. And then there's things that happen on small scales, such as spontaneously fragmenting flux elements. And also we observe collisions and cancellations. And these ovals, you know, basically are, you know, unlocking the mysteries underneath each of these ovals each one is a big project, more or less, because you need to know lots of things about, for example, the solar dynamo, how flows and fields interact via magnetoconvective processes and things of this sort. So let me just highlight these lower 3 items having to do with the smaller scales. And so you can see that if you just take a cutout of HMI magnetograms, which is here, you can basically see that the field is very blobby and clumpy. And as the convection structures the field, you can definitely see, you can make out the outline of some supergranules sized things. So they're of order 30 megameters across. And this movie is, has about, 8 to 10 of them across, more or less. So, and you can see that they evolve on the time scales of hours. And then this is sort of analogous to what happens on even smaller scales. And so if you look at higher spatial resolution, such as what we get from SOT on Hinode, in the middle here is one big supergranule, and you can see even smaller scale flux concentrations that are constantly moving around and emerging in this particular field of view. So that sort of highlights one property of the sun, and that things are somewhat self-similar once you get below a certain scale. And Carl Schreiber attempted to understand this property in terms of just, well, what if you just sort of reduce it to the fact that, well, each blob is a point-like flux concentration. What can you learn from that? And so he developed the surface flux transport model that I now use, which is based on keeping track of point-like magnetic flux concentrations. And so each point is assigned a certain amount of flux, and it has a latitude and a longitude on the model photospheric surface. And these points get moved around with time. And so if this were pointillism, if this were a pointillist painting, then I guess that makes Carl a Dutch master of some sort. But anyway, but embedded in Carl's surface flux transport model, we have schemes that define how flux fragments and collides and disperses based on the observations that were done, here on the Lockheed group, mostly during the MDI era, I believe. There's definitely some correlations with the amount of flux in the element and things like how likely it is to fragment and how mobile these concentrations are. And so all of these things are sort of parameterized and built into this point-like surface flux transport model. In 1997, this was described by Carl Schreiber as magnetochemistry, and I've also heard him describe this as an atomic model, because each of these flux concentrations is sort of one atom in a whole system of things. So back to my ovals. Let me just also say one quick thing about the flux emergence process, and that is that that there appears to be a distribution. So if you try and identify the emergent bipoles, which is fraught with some observational difficulties, I must say, having tried to do it myself. One of which is that you sometimes get different answers depending on the spatial resolution of the data you're using. But after you try and account for that, which is what Mandi Hagenaar et al. Have done here, you can try and define what looks like a distribution of emergent flux from active region size scales to all the way down to the smallest ephemeral region size scales. And so as you can see here, there's this basically what looks like a power law from the very largest things on the right, the active region size scales, and we know that there's a spectrum of active regions. And then there's also, as you get to smaller scale bipoles, there's even smaller things. And they argue that this turn down here is actually just due to spatial resolution. So at some point, your spatial resolution merges your emergent bipoles together, and you can't really observe them as readily as you need to in order to determine the emergence rate. There's also a gray band in this plot, and that basically shows the sunspot cycle dependence. And so when the activity level is high, of course, you get more of everything. When activity level is low, then there's a drop off, but the drop off is bigger for the active region size things, not surprisingly, than it is for the ephemeral region size things. And we know that there must be a constant emergence of ephemeral region sized bipoles, just because convection, based on the movies I showed earlier, are very good at very quickly moving flux concentrations to the perimeters of the convection cells. And so if you weren't constantly emerging new bipoles, then you'd quickly clean out the interiors of granules and supergranules. And you wouldn't see what we observe. And so that is what I think one of the big results of that sort of that era of trying to understand the magnetic carpet, as it's sometimes called. So anyway, if you put all that together, then you can make a movie of surface flux transport. And so that's what I'm going to show here. Let me start the movie. Yes. Okay, so it should be playing. And as you can see here, so this is a completely simulated sun-like star. And the time index is in the lower right, so you can sort of get an idea. It's set to have basically 11-year sunspot cycles. And you can see in this image, it's actually putting in a lot of active regions, which harkens back to things like sunspot cycle 22 and 23 activity maximum. There used to be a lot more active regions. I should say that this is actually showing all 360 degrees of longitude across, and all latitudes as well. And so you can sort of see now that the polar fields are building up in the usual fashion. And then I'm going to now drag the slider so that many years go by, you can really see that, okay, there's minimum. And then if you look carefully, you can sort of see the rush to the poles, although maybe this projection makes that somewhat more difficult. So it's important to think about this stuff on slow and fast timescales, as well as small and large spatial scales as well, I would say. So I view surface flux transport models as a way of building intuition, more or less, because it's just a 2D model. We're only modeling the evolution of flux on the photospheric surface. And a lot of the results of the model depend on what you stick into the model. And while we try and be as faithful to the observations as possible, if you remember my laundry list of constraints, there's always some detailed correlation that you're probably not representing exactly right, and it's unclear really what effect that has on things you're really interested in, which in my view, sort of like one of the more useful things that you can study with surface flux transport is the buildup and the evolution of the polar fields, which is taken on more importance of late because of the pretty well-established correlation between polar fields and the activity amplitude levels. So in the model, however, we can mess around with various inputs, for example, tilt angles and variable flow speeds and such, and see how much of a difference it makes and try and gain intuition that way. And so one thing that I did, which unfortunately I haven't actually published this, but I'll show it anyway, is to just look at what the stochasticity means. And so what I'm going to show you are the results of some synthetic cycles where I used, if you remember the distribution that I showed earlier of active region emergence, basically I'm just drawing emergent bipoles from that distribution and sticking them into the model and seeing what happens. And I've done this for a bunch of different models just to see what happens. I mentioned polar fields, and I'm sort of going to use polar fields as a barometer of evaluating the model. And of course, the conventional wisdom is that the polar cap flux forms as a result of the tilt angles of the collection of emergent active regions over the course of a sunspot cycle. And then, another factor is once you have active regions emerging in a tilt that are tilted, Then you also have some cancellation of the leading polarity fluxes across the equator. And so that leaves a pattern of trailing polarity flux to be moved poleward by the meridional flow, as you can sort of see in this. So this is cycle 24, and you can see these streaks of these poleward streaks of a preferred polarity over the course of this particular sunspot cycle, which canceled out the original red polarity that used to exist in the preceding solar minimum and replaced it with a blue polarity by the time that the activity cycle ended. And the southern hemisphere was analogous, but with opposite polarities. So you can definitely see these streaks that have been mentioned many times already here. And so in my view, the polar fields are a pretty good way of assessing these models. As far as secular trends are concerned, so here's one model that I ran with the Shriver surface flux transport code. And so on the right, you see 3 snapshots separated by about 5 years each time. And so, separated by about 11 years each time. These are successive minima, more or less. And so you can see that here, these are latitude, longitude maps. You can see that the North Pole is blue here and the South Pole is red, and then the next minimum, those poles are reversed, and the minimum after that, these are reversed. On the left, this plot shows the absolute flux integrated across the whole model as a function of time. And so you can see there's a number of activity cycles here. There's at least a dozen. And of course, it goes up and down as the activity level goes up and down. The small curves at the bottom here show the polar fields that are poleward of 60 degrees in each hemisphere. No, just the dashed line is just one hemisphere. And so you can see that for that one hemisphere, the dashed line basically oscillates around the 0 level with time. Now, running the same model with the same initial condition and the same parameters, you can actually find models that do this. So what's happening here is that just because of the particular sequence of outlier events, for example, you might call them rogue active regions, but often what happens is an active region will emerge with, maybe at an unusually low latitude, so that it straddles the equator, for example, which does occur on the sun occasionally. But if you have like the right sequence, and here you can sort of see that there's, some varying levels of the activity amplitude. So often this can happen if you have a weak cycle followed by a strong cycle, followed by another weak cycle, followed by another strong cycle. And so that you're constantly, over that set of four sunspot cycles, you're constantly advecting preferentially one polarity poleward. Then you can actually find these drifts away from the 0 level in the polar fields, as shown here by the dotted line. And that's interesting. I'm not too convinced this has ever happened on the sun. I mean, we don't really observe the poles very well. And of course, going back in time, we only have proxies of the polar fields. But if you look at most of these proxies, they seem to indicate that there's a pretty, that there's always a noticeable cycle occurring, going back, hundreds of years. And so I'm not really convinced that this ever happens in the sun, or at least it hasn't happened recently. So if that's not happening, then that means that there's something a bit askew in our understanding, which I think is interesting. So anyway, I ran this model about 20 times, and so here are all 20 charts like that. And since you can't actually see them, I've overplotted them on this figure here, and you can sort of see by these dashed lines the range of polar fields that emerge. So I see Leif has his hand up. So Leif, do you want to ask your question?
Undo here. Yeah, there we go. The question of polar field reversals. The polar field polarity has a signature in the interplanetary magnetic field, which has a signature in the geomagnetic field, which we can measure. And we know that since 1844, the polar field has reversed in every cycle. So that's an observational fact. Okay. Now, before that, we don't know, but at least we have But there is another way that potentially can give us that information. That is the variation of cosmic rays. That shows a strange pattern oscillating between a sharp peak or a flat top. And that also changes when the polar fields change. Unfortunately, the cosmic ray data is not quite good enough because they are model dependent to show that, but maybe we can get some information on that in that way. But certainly it is a fact, an observed fact, that the polar fields have reversed in every cycle since 1844. So.
Yeah, so yeah, sorry. So yeah, I think that, so that means that you know, the surface flux transport model is sort of illustrating somehow that there's, and this is, you know, maybe if I state it state it this way, it's not terribly surprising, but there's definitely some feedback between what the sun chooses to emerge and how it chooses to arrange, for example, the meridional flow, for example, could easily, or the tilt angles. We were talking earlier about correlations between cycle amplitude and tilt angles. Tilt angle in particular, you know, really does have a strong effect on the resulting polar fields. But so too does the meridional flows, and now we have you know, sort of 2.5 cycles of helioseismic measurements of meridional flows, and we know that there's some variation in those. And so there must be. I mean, it's not really that surprising that there's some that there are feedbacks between the fields and the flows, and the flows feed back onto the fields, and so that really is not captured in these more kinematic models like the surface flux transport model. So that's one reason I say these types of models are useful for gaining intuition, just because, you know, you only sort of realize that something is askew in the model when you do things like what I've done here. So anyway, let me move on. So I kind of just said a lot of this, but anyway, you know, I've done some experiments with cycles having, you know, trying to keep some things constant while adjusting other things. And it seems pretty clear to me that for cycles with the same length in time and same amplitude of solar maximum, same emergence properties as given by that distribution I showed earlier, factors that influence the polar fields are tilt angles. In general, larger tilt angles lead to more polar flux. The dispersal properties can have an effect. So if the flux is able to move around more readily, then you tend to cancel more. There's more net cancellation across the equator, and that leaves a net, as I mentioned earlier, trailing polarity flux that gets advected poleward, and so you tend to have more stronger polar fields. There's also things like the fragmentation rate, and so if you have in this atomic model, if you have higher fragmentation rate, that means that you know, you'll end up with a population of smaller elements which tend to be more mobile, which tend to be more, you know, a lot of those are more likely to cancel across the equator, and that leads to stronger polar fields. And so, and I see Robert has his hand up, so I assume you have a comment or question, or you're going to throw some tomatoes at me or what. So we'll see what happens. Robert.
And my question was from before. I was just wondering if, for example, a connection between the activity level of the next cycle and the polar fields wasn't an alternative possibility to the meridional flow variations, for example.
Right. So the cycle amplitude, it's interesting. I don't actually, I mean, I think that, so I mentioned earlier, I think in my long laundry list of constraints, that there's a correlation between the cycle amplitude.
Yes, and would this be enough
length of the cycle? And so to me, that says that kind of the same amount of flux is being introduced onto the photospheric surface within each cycle. So I'm not sure that the amplitude by itself.
Okay, so we should talk later.
Yeah, we should. Okay, because like I said, this is this is ripe territory for more of these feedbacks, I think. Okay, so are there any more flux transport questions? Because I'm about to move on to evolving models that use the vector magnetic fields. I'm not monitoring the chat at all, so raise your hand. Okay, last chance. All right, forging ahead. So what about vector magnetograms? And so, HMI has been providing, ostensibly providing full disk vector magnetograms for 12.5 years. And then, of course, there's other instruments that have been providing vector magnetograms as well. So, for example, SOLAS. And then there's limited field of view instruments that provide vector magnetograms for different patches of the sun. So presumably they contain more information, and putting aside all the issues associated with actually determining the vector magnetogram from, because typically you have to do some sort of spectropolarimetric inversion. If now that we have vector magnetograms on a regular cadence over the full disk from, say, HMI, how can we best use them? So because they encode more information than the line of sight magnetograms, in principle, at least in some locations, they can be used to better estimate physical quantities such as electric fields and pointing fluxes, at least pointing fluxes through the photosphere. And so the idea is to capture some of this additional information and try and understand how it affects the global model. So I'm now venturing into territory that is work that I did not do myself. We're leveraging the detailed work that the Berkeley Theory Group has done over the years in terms of trying to figure out electric fields given both flows and fields, vector flows and vector fields on the photosphere. And so the three main ingredients are in this scheme are a time series of vector B horizontal flows from a local correlation tracking algorithm, and also a time series of line of sight velocity from which you can determine the third component of V. And if you use all of these things together, there's a scheme that they call PDFI, which stands for toroidal, oh gosh, I can never remember what this acronym stands for. I should never try to spell it out, so I won't. Okay, so PDFI, poloidal decomposition, FLCT is the local correlation tracking algorithm, I is induction, I think. Bill, you should feel free to correct me. But anyway, this scheme allows you to infer what the electric fields are in the photosphere given these inputs. And the main idea, if you move behind, sitting behind this figure, are these equations. The first thing you realize is that Faraday's law exists. So the change of B with time must equal the curl of E. And you can decompose this into two potential equations, a poloidal potential and a toroidal potential. And using the observations to constrain the script B's and script J's, you can actually figure out what E must have been to give you the observed change in B. So, and if you look in the PDFI papers, so essentially what you're trying to do is look at the change of B and figure out what E is. And so on the surface, you can just see from Faraday's law that involves sort of uncurling this equation. But when you uncurl that equation, you introduce a constant of integration. And a lot of work has been done to try and understand how this constant of integration affects things. And so ideally you want to be to have consistent values of all of these things. Anyway, there's a lot of details associated with PDFI scheme, which I don't really have time to go into. And there's lots of detailed papers written on this. So I am going to cover these equations back up and move on with the talk. Now, let's assume that all of this has worked amazingly well, and you have a time series of E. So what can you do with it? So one thing you can do actually is to create what I what Marc Chung has termed a constrained surface flux transport model. So ideally, you want to create a global model of BR as a function of T from the photosphere using the inferred EHs, which are the horizontal electric fields. Now, in practice, you can only really infer the horizontal electric fields in places where the magnetic field is strong, and so that effectively means active region patches. But the large-scale flows, such as those that involve the differential rotation, U theta, and the meridional flow, U phi, you can also determine what the corresponding electric fields are for those. And so there's this model that we spent time developing as part of the CGEM project that does this. So again, here is Faraday's law, again, in non-dimensional units because the C is missing. And here is the magnetic induction equation. And so you can sort of see there's a correspondence between these two things. In particular, in the induction equation, everything on the right is the curl of something. And so that allows you to sort of just so ideally, if you have good electric fields, you can just sort of plug them into this equation and take their curl and evolve B, at least B on the photosphere. Oh, thank you, Bill, for putting that. I just saw the message in the chat pop up. So anyway, okay, so now that means you're taking curls. And so as far as a numerical scheme used for taking curls, we have this staggered grid, which means that the places where BR is known, so the red dots are BR, are offset from where E theta and E phi are known, which are the ribs surrounding each cell center here. So then it's just simply numerically, it's just simply a matter to determine the evolution of BR, dBr dt. You just simply take the curl around each, just add up the four values of the E's, and you get dB dt after accounting for the area, of course. And so this scheme was called constrained transport by Evans and Hawley in 1988. And so that's why Marc Chung called this type of model a constrained surface flux transport model. I'll note that it has one interesting property, and that is that it's what I call scale agnostic, which means that if you have places where the spatial resolution of your model is less, then you can actually just take curls around bigger things and get BR in, an average BR covering this larger region here. And so that's kind of neat. And that allows you to maybe, for example, have higher spatial resolution in places where E is better determined, and lower spatial resolution where the E fields from, say, the bulk flows is smoother. And when you do that, if you just drive a model of BR as a function of time using electric fields from active regions, you get something that looks like this. So this is 180 degrees of latitude by 360 degrees of longitude. This is a synoptic map from March 18th, 2014. And when you start the movie, you'll eventually see that there's slow evolution in some of the active regions. So the movie basically lasts one Carrington rotation, I should say. And you can sort of start to see the outline of the patches actually. It's happening very slowly, but over time, I assure you it's changing. And as the sun rotates, you get further and further east in the patches that get updated. So actually, this scheme seems to work pretty well. If I were to run this model for years instead of months, like I said, this movie is just 1 month basically. You would see some advection poleward, but it's hard to see that sort of stuff in a movie that only lasts for 1 month. So I'm going to drag the slider a bit so you can sort of see how you can sort of now get a better idea of how the fields evolve. And then, oops, sorry, let me go back to the end. The other thing I would point out is that you can definitely see these squares being sheared out by the E fields associated with the differential rotation profile that we put in as well. So there is the E fields are sometimes noisy, especially in the weak field region. And it's also interesting. We've definitely found that over time, there's some flickering of the background. So you can see how this square is like slightly lighter hue than the surrounding field. So I know that that there was some detailed investigation into that, which I'm not sure we completely understand it yet. The other thing I will say about this type of model is that I know that George Fisher, in our discussions with him, had some ideas on how to create a global model of evolving vector B at the photospheric surface, driven by the horizontal, or driven by the vector electric fields that get inferred from PDFI. But that was, we sort of ran out of time in the CGEM project, so we never, unfortunately, didn't make much progress in that. So, in any case, I should also say that as part of CGEM, we do have time series of electric fields for all the active regions in the HMI era. So, if you want to dig into the electric fields, those data are publicly available from the JSOC. And so I believe that the data series is organized by time and by active region number. So if you're interested in this sort of thing, then the electric field data are available. So let me wrap up here. There's lots of high quality solar data these days, and kind of importantly for things like trying to understand the dynamo, we now have, counting the MDI era at least, we now have a lot of magnetogram data, or at least line of sight magnetogram data, spanning the last 25 years, more or less. So that's great. The fast models, and I put these 2D models are fast, of course, just because anything 2D is much faster than anything 3D, do make use of a fair amount of this data, and they enable lots of different types of investigations to occur. And we've heard a lot about these things today. Probably the future involves a lot of data-driven models, and I know that the coronal magnetic field people that I hang out with really like data-driven models, just because I think there's an increasing understanding that the coronal field has some memory to it, and so you can't just take a single magnetogram, even a single vector magnetogram, and get it. I mean, like, certainly you can probably do it on occasion, but you can't reliably take a single vector magnetogram and get like a perfect model of the coronal field just from that. I think you have to understand the prior evolution well enough to be able to do that. And so in combination with these data-driven models and our increasingly better ability to measure things in the corona, we now have more spectra of coronal lines than we used to. There's the MINEX called Muse that we're building here at Lockheed is going to provide even more spectra over a greater spatial coverage. So I think that what we learned from the photospheric data is going to be really important. Anyway, thanks for your attention, and I'll turn it back over to Bill and Aimee.
Thank you very much, Marc. Questions, Lee?
Yeah, I have one final comment. I cannot start screen sharing, so you gotta go. There we go. Okay. Try again. I want to close this thing by referring to Alfvén's Nobel acceptance speech, and his comment here that it's only the plasma itself that does not understand how beautiful the theories are and absolutely refuses to believe them. This is still valid, so we should keep all that in mind. So, and having listened to the talks today, I have a feeling that there's some disagreement about the very basics of these things. What are we actually observing, and how is the long-term behavior of all of that? I here remind you of what Roger Ulrich said. So this is my final comment on that. So keep in mind this problem here. All right, so there we go. Let me see, close the screen. Okay.
Okay. Thank you. So there was a lot of chat actually in the Jam boards. Todd, you had a couple of questions. It looks like they mostly have been answered, or? Oh, you need to unmute.
Yeah,
Sorry.
working on it. 2 buttons at a time is always trouble. So there was this interesting what looked like a gap in the number count of the ephemeral regions versus the active regions, and then Robert Cameron showed me another paper, which I haven't had time to read, obviously, which shows a smaller gap between the size scales. But it might be interesting to look again now that we have HMI for as long as we do, for features in that sort of different zone between the ephemeral regions and the active regions to see if there's anything going on there. I'm not sure exactly what it would tell us, but it seems like it either ought to be related to the fact that things aren't being created at that size scale, or that they aren't able to get to the surface at that size scale, or maybe something else altogether. But thinking about there being, this was sort of suggested to me by an earlier comment from Robert about there being sort of a continuous spectrum of a power law spectrum of magnetic field structures of different sizes. So if we see a gap in that, then it seems to me it's got to be telling us something, if there's one.
I would say that it's entirely plausible to me, or it seems reasonable that there might be a little bit of a dip if there's a distinct small scale dynamo and a distinct large scale dynamo. The gap may be evidence of the place in the middle where the dynamo action is just in a transition between these two different processes.
But at the moment, the gap is just people haven't measured it.
Yeah, that's right.
Yeah, and so from this, suddenly, if there's a real deficit of those events, super interesting. And yeah, but at the moment, the gap, which is an order of magnitude, is just no one's measured there.
Sounds like a project for somebody.
Okay. Any other questions? Yeah, sorry.
Well,
Go
I
ahead.
have a
Aimee.
very simple one. What is the smallest size scale of emerging flux that you incorporate into the surface flux transport models? And do any of them differ in the smallest element incorporated?
So for the Shriver model that I'm running, the smallest is, that's a good question. Usually, so it's related to okay, so in the Shriver model, I talked a little bit about one of the atomic, quote unquote, atomic processes is the flux collision. And the model decides that two flux concentrations have collided when they're within a minimum separation distance. And so that distance, which effectively defines the spatial resolution more or less, because the model will combine neighboring flux concentrations that are separated by less than that particular distance. The model, I think, uses a distance of maybe 4 megameters. Can that be right?
Okay.
It's 2 to 4 megameters. It's kind of of order like 1 or 2 granules, I think.
Wow,
so
that's really small. I didn't expect that. Okay.
That means that the sort of smallest ephemeral region is going to be actually pretty big. I mean, because we do see structure smaller than granulation. We can see, with SOT, for example, we've seen structure on subgranule scales. So yeah, anyway, this model is still not going down to the spatial resolution of the data yet.
Okay.
Okay. Yeah, I mean, Mark, back to the acronym. It is confusing, and I can never remember it either.
Well,
I mean, it's
a
basically
meta acronym.
Yeah.
The letters in the acronym themselves correspond to different acronyms.
I know they do. They're like an acronym on top of an acronym, right? And so for those of you that are not familiar with it, the idea is actually really simple. So what you do is you invert Faraday's law from a time series of vector magnetograms, but that problem is underdetermined, right? So you need to add more information to get it to get a better result for the electric field. So we had simulations, these old simulations of emerging flux tubes through the convection zone, and then we applied this technique, the colloidal toroidal decomposition, to that synthetic data, and then added other observations in order to get the electric fields to match. And the other observations that we used were the Doppler flows, local correlation tracking applied to magnetic elements, and one other one. But anyway, so it's stuff piled on top of one another, but it was just to make sure that you got the best result for the electric field that you could before you applied it to observations. And then once it was applied to observations, then Marc took both Marcs took the extra effort of putting it into the flux transport in the model to be able to advect the vector magnetic field over the surface. So hopefully I characterize that correctly.
Yeah, we haven't really implemented the full vector B transport model, but we were just making sure that the horizontal electric fields could inform the evolution of BR.
Gotcha.
But yeah, that'd be really cool, I think, is to have an evolving vector. Whether it would mean anything, I don't know, but yeah, it would be really nice to see if we could get anything out of that.
Great. Well, we're at the bewitching hour here. So I want to thank everyone for showing up today and participating in the discussions. I apologize myself. I was a little overwhelmed. It was hard for me to keep track of Slack and the Jamboards and the Zoom chat and all at the same time, but we did, and there were a lot of people keeping track of stuff, so thank you very much. Aimee and Shay, I'll bet you guys were the ones that were moving all of the squares around and so forth. But the point is I hope the Jamboards will be useful. Were useful today, but I hope they become useful in the future. We're going to keep them open. So if there were any discussions or questions that didn't get addressed during the session today, Aimee and I will try to organize these maybe a little bit, but we'll keep them online. And hopefully, the speakers might check back in, and if there are additional questions or questions that haven't been answered, they could post a note or whatever. And if there's a discussion that was unfinished, we can finish it at our leisure. So hopefully, I mean, the Jamboards are a little bit awkward, but they're also pretty easy. So hopefully you found them useful, and we'll keep them going. Leif, you have a question?
I think that's just applause.
I was just applauding.
Oh, okay. All right, folks. Thank you, and enjoy the rest of your Friday. And this concludes the October theme workshops of COFFIES, and we'll do something similar soon. Take care, everybody.
Okay, thank you, everyone.
Bye. Good job, guys.
Bye.
Thank you. Bye.